In this opportunity, we are going to talk about the entropy changes in chemical reactions. And basically, that's how you can use the entropy and entropy tabulated data to calculate changes in entropy for a particular reaction. So far, we've been dealing with the Gibbs free energy, and to calculate free Gibbs energy, you need the enthalpy of a reaction and you need the entropy of the reaction. But at this point, we are going to focus our attention on how to calculate that entropy for a given reaction. Okay, so before we were assuming we already have the entropy for a particular reaction. In this case, we are going to calculate it given proper data. So one of the things that we have to review here, and this shouldn't be completely unknown for you, because we back in 170 for thermochemistry, when you were working with enthalpies, then you also have to define standard state. So this should be more of a refresher, okay? But in a standard state is basically what is or in what form you can find a substance in a given set of conditions. And it's standard state because those conditions will be fixed for every single substance. Okay, so that you can have a kind of normalized data for all the compounds. So you try to make all measurements, if possible at all, under the same conditions so that you can use those values directly. So what a standard state is for a particular substance will depend on those conditions, and then it also depends on what state you are talking about. So if you have a substance that is normally in the gas state, then under what conditions that gas would be considered as standard state. So that comes with, for example, for gases, you have that gas has to be a pure gas and it has to be at 1 atmosphere pressure. If you have, let's say, oxygen, okay, oxygen gas at 1 atmosphere pressure, then you would consider that oxygen at standard state. When it comes to solids or liquids, remember, gas is, let's say, not condensed state, and liquids and solids are condensed states, okay? We are here also at 1 atmosphere of pressure, so that's kind of standard for every single substance that you're gonna use. But in this case, in particular for solids and liquids, you also define a temperature. Well, for a gas, you can also define a temperature, but usually here for us, for practical purposes, that standard temperature, so to speak, is going to be 25 degrees. So normally what you're going to find in tabulated tables, it's that those values, in this case entropy values, will be tabulated at 1 atmosphere of pressure and 25 degrees Celsius. If you are working with a solution, then the concentration of whatever it is that you are using there. And remember, if it's a solution, it could be the substance that is dissolved in that solution, could be in any state, could be a gas, a solid, or a liquid that is dissolved in something else. That concentration now has to be 1 molar. So this is what defines a standard state for different substances. We are not going into specific of what substance, it just depends on what state of matter that substance is normally found. So now we have a third law of thermodynamics. We have already reviewed the first one, well, not in this class, but the first law of thermodynamics is that the changing energy for the universe is constant. Okay, so the change is 0. That's 170 material. We have the second law of thermodynamics. That's the one that we've been dealing with here. Okay, so that for a spontaneous process, the changing entropy for the universe has to be positive. Okay, so it could be positive, it could be negative. Okay, but if it's spontaneous, then that changing entropy has to be positive. Processes are driven towards a more disorganized state, okay, so to speak. Now, the third law establishes, well, there are certain conditions in which you can make the entropy of a particular substance equal to 0. Going just a little ahead of time here, all entropy values. No, we are not talking in terms of changes in entropy. For example, if we have, let's say, the enthalpy of formation for methane, okay, then this is a change in enthalpy that you obtain for the formation of methane. There is no such a thing for substances. You just have a total entropy for a substance, not a change in entropy. Okay, so this is, in a way, that heat that is associated with the formation of methane is a change in energy, change in enthalpy. There is no absolute enthalpy. Okay, but when it comes to entropies, then you can have an absolute entropy for any given substance. And that absolute value of entropy, it's always positive. Okay. However, there is only one one situation in which you can have the entropy for a particular substance equal to 0. There is only one condition in which you can obtain that. Okay, and is this one that you have here. You must have a perfect crystal at absolute 0 Kelvin. Okay, this absolute 0 refers to temperature. If you can have a perfect crystal at 0 Kelvin, then the entropy associated with that crystal is going to be 0. Okay? So, but, I mean, we are talking here about pure perfection. Okay, a perfect crystal. And you might imagine how frequently that happens, right? So that's a very rare situation, perfect crystal and 0 Kelvin. So that's the only case that when you have an entropy equal to 0, everything else will have a given value of entropy, and that value will always be positive. Okay, so do not forget this. The absolute entropy for substances is always positive. Unless you manage to produce that crystal at 0 Kelvin, then the entropy is going to be 0. Is it going to happen? Probably not. Okay? So, remember, entropy has to do with randomness. Okay? And anything that increases the randomness of any system will be favorable, will have favorable, meaning that it's going to be tending to be a spontaneous process. Okay? So that's why if you are, in this case, if the entropy of this thing is positive, you are increasing randomness. Okay. Yeah, let's use something that might be more familiar, especially if you have children. So increasing is not very scientific, but increasing the mass. Okay, so making things more disorganized. Okay, that's basically a everyday life kind of thing that you can relate to randomness. If you are increasing the disorganization level of your system, the delta S is going to be positive, and that's going to be a favorable process to be spontaneous. Now, in the other case, if the entropy of the system, the changing entropy of the system is negative, you are decreasing randomness. And to use something, especially what particularly moms do with their children, if you are sort of cleaning the mess, then that's associated with a changing entropy negative. So is it gonna go spontaneously? I mean, the mess is gonna be spontaneously fixed? No, you have to provide some energy. You have to provide some effort to clean the mess. So that's why that process is not favorable to be spontaneous. The other way around, it is, but changing entropy negative, the process is not favorable. Okay? And this is one equation that you need to get familiar with. This should be familiar because it's pretty much the same that you use when calculating enthalpies of reaction when you have enthalpies of formation. It's the same thing. So, well, the same thing, but with entropy. The bottom line here is that I want you to keep on your mind, in your mind, that the shape of this equation is always products minus reactants, and then you have to account for the number of moles of products and reactants that you have there and the enthalpy, so you need to multiply the enthalpies by the corresponding number of moles that participate in that reaction. Okay, so for that purpose we use the absolute entropies. Those are that's data that you can find tabulated on tables. For practical purposes, I'm probably going to give you the values, but remember, these are values. These are standard absolute entropies, so they are determined at a standard state conditions. The ones that we mentioned at the beginning, the standard entropy for a gas was measured or was determined at 1 atmosphere for that gas, and then you have the value, and well, you want the same thing for all the substances according to the state they are normally found. It's an extensive property, meaning that the more you have, the higher the entropy will be associated with that material. So that's why you have to multiply by the number of moles that you have in the reaction. That's why it comes from there, because of the fact that it is an extensive property. Okay, and it's that entropy that you use will be specific for that particular substance at that particular set of conditions. Whatever the conditions are, whatever the substance is, whatever the form of that substance is. So you change a little bit that state. If you change, let's say, the crystalline structure, you are changing the entropy for that particular substance. So how can we relate when we are using these standard values or these absolute entropies for any substance? How can you relate about what are the relative values? So to have an idea, right? So on what depend those values? So one of the things that you have to consider, we discussed this at the qualitative level. For example, if you have a solid and a liquid, the liquid will have a higher entropy than a solid, and the gas will have a much larger entropy than the liquid, than the solid. So now we are looking at this at a more quantitative point of view. We have two, this is the same substance, is water. One is in the gas phase and the other one is the liquid phase. Qualitatively, we already knew that water in the gas phase will have a higher entropy than water in the liquid phase, but now we are assigning numbers to those. Okay? So whenever you have the same substance and you're comparing the same substance at different states, then different state of matter, that is, then the gas will be larger than the liquid will be larger than the solid. Okay? These are some examples of, excuse me, of standard absolute entropies. And as I said before, they are standard entropies, and that's why you have this temperature. This is 25 degrees Celsius. And out of this table, the one thing that you may want to notice is that, well, we have gases here. And if you look at the values of the gases, well, they are all on the hundreds. These values are generally larger than what you have here. Okay, and you can also notice that there are some of them. For example, here, if we look at hexane as a liquid, it's a liquid. But if you compare this with some gases, for example, argon, well, that liquid has a larger entropy than hexane. So it's not only the state of matter that controls the absolute value of entropy, there is something else going on, and we're going to review all of that, okay? So, but in general, gases will have larger entropies than liquid, and liquids larger entropies than solids. So here, again, just for comparison purposes, we have iron chloride here, and it has an entropy value of 142. If you compare that to water, which is a liquid, well, that solid has a larger entropy than water in the liquid phase. There is a reason for that. Okay, so again, when you're looking at states of matter, generally speaking, gases larger than liquids and liquids larger than solids, but there are other factors contributing to the entropy that must be taken into account to be better able to predict what is the changing entropy on these substances. Okay, so the first one again is the state of matter. The next factor that affects the entropy is the molar mass. Okay, and here, generally speaking, the larger the molar mass of a substance, the larger the entropy is for that substance. Okay, and the reason for that, remember, entropy has to do with how many different ways you have to dissipate energy, how many different microstates you can have for a particular substance. So in this case, we're comparing, we are increasing the molar mass of these gases, and these are monatomic gases. Let's start with these. These are monatomic gases. These are noble gases, monatomic. You are just comparing one single atom to another, and then you see that the entropy will increase as you increase the size of the atom. Now, why is that? Why can you have a larger entropy if you are just increasing the size of the atom? Well, you have to think about this, right? What's helium? Helium, the atomic number for helium is 2. The atomic number for neon is 10. So that means that in this atom you have 2 electrons moving around the nucleus, and in this atom you have 10 electrons. Now you're increasing the number of electrons, and this is again another oversimplified picture of what's going on here, but having a larger number of electrons increases the number of possible microstates that you can have for that single atom. You are just adding more ways in which you can dissipate energy. If you look at argon, I think it's 36. So for argon, you have even more electrons here, right? Wait a minute, I'm not sure about this. So anyway, the point is you are increasing the number of electrons, and if you're looking at these monatomic gases, you're just increasing the number of electrons, okay? You're increasing the size, the number of electrons, you're increasing the potential number of microstates that you have to represent each one of those atoms. So that is why the entropy for these substances, in general, as you increase the molar mass, the entropy for that particular substance will increase. In a per atom basis, you are increasing the number of electrons, you are increasing the number of microstates that you can have to represent that atom. Okay, so that's the explanation behind molar mass. So if you want to kind of remember this in a different way, if you have molar mass and the molar mass increases, then the standard entropy also increases. Okay, go hand in hand. There is a direct proportionality there. Okay? Now the next factor, allotropes. And allotropes is, let's put it this way. They have different, let's call it crystalline structure. They are the same substance, it's just the way those atoms are organized is different, okay? So for example, the 2 examples that we have here is that you have diamond and we have graphite, okay? So diamond is, it's a very rigid crystalline structure. I mean, if you can see that as a 3D network of atoms interconnected with each other. Okay, so there is very little room to do anything in that crystalline structure. That's for diamond, okay? We are looking at that one. However, for graphite, that structure for graphite, it resembles more like a different paper sheets or sheets of paper on top of each other. Okay, so it's a crystalline structure, but it could be, if we can call this 3D structure. Okay, 3D crystalline structure for that matter. Graphite is more of a 2D structure. It's just a sheet of atoms, and as such they can move on top of each other. There is the potential for those graphite sheets to move on top of each other. So if you can do that, if you can move them relative to each other, then you are adding microstates in which you can dissipate energy. That doesn't happen in the crystalline structure for diamond. That network will not move anywhere. Those atoms will be fixed in place without any possibility to move anywhere. Okay, so that's why the entropy for graphite is larger, because you can add more microstates to that crystalline structure for graphite. Okay, so that goes for allotropes. Molecular complexity, that's another factor that you can take into account for increasing the entropy. Okay, one of the things that we said at the beginning was that a larger molar mass will increase the entropy. And here we are comparing argon, this is monatomic, with nitrogen monoxide, which is diatomic. So we are adding 2 atoms to that structure, right? So instead of having only one, we have 2 atoms. However, the molar mass for argon is larger than for nitrogen monoxide. Still, the entropy for nitrogen monoxide is larger than for argon. So what is the explanation here? Those atoms are smaller. Technically, you can say from the point of view that those have less, argon is 18. So those are less than, have a lower number of electrons than argon. So why is it possible that nitrogen monoxide will have a larger entropy than argon, since it has a smaller molar mass? So we have to take a look at the structure of nitrogen monoxide. So what are we looking at here? Okay, so things that we have to consider when we are looking at a molecule. Okay, they have translational motion. That means, let's say if you look at X, Y, Z axis, how that molecule is moving along those axes. Okay, so in this case it's moving along X, in this case it's moving let's say along Z, and in this is moving along Y. It doesn't really matter. The point is it can move in different directions, and because if you're moving in different directions, then you can assume that as a different microstate. The argon can also do that. The argon atom can move in that direction, can move in that direction, or can move in that direction. So in those terms, it could be the same. However, for this molecule, now you have that molecule can move around, can rotate. Okay, and by rotating, now you are changing the position of those atoms. So in one time, let's put it this way. In this case, the blue one is in the left side, and by rotating, now you can switch places, and now the blue one is on the, initially was in the left side, now is in the right side. Okay, so those are 2 different microstates. Okay, so by rotating the molecule, you are adding microstates. But if you have the argon atom, well, that atom will rotate in place, but in terms of adding a microstate, well, it looks pretty much the same. So there is no gain in microstate by that atom rotating along its own axis. Okay, there is no change in position of the atoms. There is no, you are not adding another equivalent microstate by just rotating the atom. So argon doesn't get any, there is no gain in entropy for doing that. And here, that bond that you are having in between the nitrogen and the oxygen, that bond is vibrating. Okay, so imagine that you are connecting two balls with a rubber band, and then you stretch back and forth that rubber band. That's what the bond is doing. So you are adding more microstates here. So more microstates for nitrogen monoxide than for argon. And that's why the entropy for the absolute entropy for nitrogen monoxide is larger than for argon, even if argon has a larger molar mass. Okay? Now, molecular complexity. Now, what happens if you have the same molar mass, in which in this case, well, there is no conclusion to draw just by looking at the molar mass, but now you have those molecules here, okay? And for CO, the structure of CO is this one. And you can apply the same analysis for the carbon monoxide molecule as we did with the nitrogen monoxide, okay? Just replace carbon for nitrogen here, and then you have the same analysis, okay? How about the other molecule? We have C2H4. Now the C2H4 molecule, you don't really need to know this, but the structure of this molecule is this one. Okay, and what we are really looking at here is that every of those situations that we look at here, the molecule moving, the rotation, but particularly the vibrational motion of those bonds, if you have one bond, you have all of that, okay? But now here, you have 1, 2, 3, 4, and 5 times the opportunity to have vibrational dissipation of energy in the molecule. Okay, so you are adding, again, by having more bonds, you are adding more microstates. And as such, you have a larger absolute entropy. Okay, so remember, things that will control the absolute entropy, the molar mass, the different allotropic forms, the complexity of the molecule, and what else? We have here the solution. In this case, we are looking at the same substance, is potassium chloride, but we are looking at the solid compared to the dissolved one. Okay, what are we looking at here? And I think we have already seen this before, just at the qualitative level. When you have the solid, this is a salt. When you have a solid, it's in crystalline form. And by crystalline, we are looking at a very well organized network of ions, alternating ions for that matter. But when they are dissolved, then they are solvated, okay? So that means you have potassium in one side, and then you have the chloride in the other side, and then water is going to be surrounding each one of those ions. Okay, the oxygen will be pointing in the direction of potassium, the hydrogen will be pointing in the direction of the chloride. Okay, and why is that? Because the hydrogen in water is partially positive and the oxygen in water is partially negative, so opposite charges will attract themselves. So the dissolution process in which you have that salt dissolved in water will increase the let's put it this way, will increase the mass. That structure will not be in a very well organized state. It will not be in a perfect crystalline structure. It will be all around the place, all around the flask, the container of that liquid. Okay, so that's how whenever you see a solid compared to the dissolved version of that solid, then the entropy will be larger. So now remember, it's time to start using this equation for practical purpose of calculating the entropy of a reaction. Okay. Remember that we are always using standard states. Usually that means we are working at 725 degrees. One particular piece of advice, if you remember from thermochemistry in 170, the enthalpy of formation for elements is 0. There is no such a thing for entropy. Okay, so the standard entropy of formation for elements is larger than 0, but I want to cause a little more impact here. Okay, it's different from 0. Okay, we'll have a definite value, and now we add here always positive. Okay, so keep in mind that. Now that's for the absolute entropy, and let's add that here. Absolute entropy. The change in entropy is a different story. Okay? And this is what we are going to calculate here. It's always, as I said before, it's always products minus reactants. And you have to multiply the absolute entropies for each substance by the number of moles that you have in each one of those substances. So in this particular case, the change in entropy for the reaction is going to be equal to 4 times the entropy of nitrogen monoxide plus 6 times the entropy of water minus everything that you have in the reactant side. Okay, so that is 4 entropies of ammonia plus 5 times the entropy of oxygen. Okay, remember, you are subtracting everything in the product side. Okay, so I'm just grouping them with a parenthesis. So that means that your entropy of reaction, it's going to be 4 times, and well, in this case it's not so critical because they are always positive. So 4 times 210.8 plus 6 times 188.8 minus 4 times 192.8 minus 5 times 205.8. Okay? So, and when you complete this calculation, then your enthalpy of reaction is going to be equal to plus 178.8 units, joules, mole, Kelvin. Okay? Now you have a positive sign here, and you may be asking, does it matter that you have a sign there? Absolutely. It does matter that you have a sign there. This means that the change in entropy for this process is positive. Therefore, this reaction as written, it's not favorable. Okay? So in order for that to happen, there are other factors that you need to control. We don't have information about the enthalpy, which does not allow us to calculate the Gibbs free energy, for example, to determine whether it is spontaneous or not. But in this case, from the entropy point of view, is non-spontaneous. Okay? And things that you may notice here as well, and we were doing this before, right? So there are 4 and 5, that's 9 moles of gas. You have, what am I saying? 4 and 6, that's 10. Let me take back what I said. It's positive. And I just said that negative, it was non-favorable. If it's positive, then it's favorable. Okay? If the changing entropy is positive, there is favorable, the reaction is favorable from the point of view of entropy, so it tends to be spontaneous. Okay, sorry about that, it just slipped my mind. Okay, let's do this again. So we have another reaction, but the process is exactly the same. It is going to be products minus reactants. Okay? So the changing entropy for the reaction is going to be 2 times the entropy of water plus 2 times the entropy of sulfur dioxide minus 2 times the entropy of hydrogen sulfide minus, in this case I'm not grouping them as in in a parenthesis. You can do it if you want to, you don't need to, it's whatever you feel more comfortable with. Minus 3 times the entropy of oxygen. Okay, before we finish the calculation, I want you to notice we have 2 moles of gas, 3 moles of gas, that's a total of 5. Here we have 2 moles of gas, that's 4. You are decreasing the number of moles of gas here, therefore you may predict that the change in entropy for this reaction, because you are going to a lower entropy system or a lower entropy state, then it has to be less than 0, which means it's less favorable. So let's complete the calculation here. So we have the entropy of reaction is going to be equal to 2 times the one for water, which is 188.8, plus 2 times the one for sulfur dioxide, 248.2, minus 2 times the one for hydrogen sulfide, 205.8, minus 3 times the one for oxygen, 205.2. All right? So your enthalpy, changing enthalpy for the reaction given the information that you had, is minus 152.6 joules mole Kelvin. Okay? So it's negative if your delta S, if negative, then is not favorable. Not favorable from the entropy point of view. Okay, this means that this is a reaction that potentially might require some input to for it to actually happen. Okay, but again, I would like to say that this is sort of a simpler calculation. It's just products minus reactants, and then all you need is the absolute entropies for every single substance, remembering that for elements it will be different from 0. They will have a definite value. You will not discard it as you did with enthalpies way before. Okay, so this is it for now.